Hello, hello. It's time for lecture 18. 1, 8, 18, 1, 8, 18. Yes, 18. What a magical age. What an awesome lecture this is going to be. Why? Because we've gotten to this part where we now understand that you wind up creating electric generation, right? By spinning stuff around, whether it's a motor or a generator, you can generate electric current or you can create power. It's all kinds of wonderful stuff. And we understand now that there's this thing where your circuit is sending electricity in and out, right? Up and down, positive and negative, positive and negative. That's really, really important. It's very, very interesting. So we understand now, right, that we have, hang on just a second, I'll be right back. Hi, I'm back. Thanks for your patience. I know no time passed for you on this video, but I just took care of some stuff. Here's the story, right? Remember that you figured out that in DC circuits, right, you could store energy in capacitors, right? 1/2 CV squared. And now you learned that in AC circuits and alternating circuits where the current flows, the voltage, the electromotive force, I should say more accurately, keeps going positive and negative, right? Then you can have an inductor store energy, 1/2 Li squared, which is what we talked about at the previous lecture. So alternating current has its parallels with the direct current, right? Although we're talking about not parallel circuits necessarily, but series circuits or parallel circuits, and they have their own rules. All right. And so this is important. That's why you will often see inductors as part of an important part of alternating current, AC circuits. Now, what we're going to talk about now is what happens when you put an inductor in a circuit. All right. And then later on, you'll see that you'll actually, when you put inductor circuits and resistors in a circuit, something cool happens. And if you put an inductor and a resistor and a capacitor, you get something else that happens that's cool. So the voltage and the current and so forth, all of that is really neat. Okay. And it's worth learning. This is like the home stretch for our understanding of circuits, right? Because alternating current circuits with that electromotive force and the magnetic field and the electric fields, these circuits are really important in our daily lives, and we use them all the time. And like I said, it powers our civilization. But beyond that, once you are getting these concepts and like the most practical parts of it, we're going to slide over to the next stage when you see that you have an electric field and a magnetic field, and what happens when they interact. If you wind up sending your electric field and magnetic field kind of alternating back and forth throughout, you wind up getting an electromagnetic wave. Oh, wow. Electromagnetic waves are light, radio signals, infrared, ultraviolet, gamma rays, X-rays. Great stuff. Can't wait to get to that too, because there's a whole nother realm of amazing stuff when we're starting to talk about electromagnetic waves. But right now, let's wrap up electromagnetic circuits, electromagnetic activity, electricity and magnetism in a sort of daily, real practical kind of life situation. Okay, let's do this. Once again, we go back to the textbook here, which I think does a very good job of talking about the electromagnetic parts of things, right? And we just finished in the previous lecture talking about inductance and the 1/2 Li squared. And just for reference, remember, if you go to 19.7, the energy stored in capacitors, that was from earlier in the semester, you have energy capacitors, 1/2 CV squared. Same sort of concept, right? Same sort of parallel ideas, which I want you to keep in mind as we go through, because like when you're thinking about electricity in the long term, I want you to understand the concepts, right? As much as you can do the calculations, which are important, I want you to know the concepts even more, because that's what matters down the road. When you are that medical professional, or when you are that biologist, or that environmental scientist, or that engineer, or whatever that you're going to do, right? That chemist, make sure that you understand, or, politician, or whatever you are, history person, government person, language person. If you know this stuff, you are so much far ahead, such good shape about understanding the world. And so that's why I want you to know this, right? Calculation, very useful, but the knowledge, extremely important. Oh, remember what happened when you had the current, right? And we had the resistor and the capacitor together, you add an RC circuit, and then you have a decay time. Oh my gosh, hey, this looks super familiar, doesn't it? This energy stored in capacitor thing, this chapter 19.7, sounds like we got to get back here and just remind ourselves real quick, okay? Going back to earlier in the semester, I know it's like, what? You're looking at stuff in the past? Yes, because it's actually very, very useful. What we want to do is go down to circuits and DC instruments and things like that. Okay, so let's go down here into chapter 21. And remember, with resistors and series and parallel and resistors, DC circuits containing resistors and capacitors. Let us remind ourselves what the situation is, right? We have the RC and we have an RC circuit. What happens is that when you discharge, right, you have all this capacitance of this charge sitting in the capacitor and it discharges through the resistor. Whoops, I just had another bounce back. That was weird. That's okay. And you see it discharges on the resistor. You have the RC circuits, right? And you have a discharge across this picture. And you notice what happens. The voltage on the capacitor, when you're charging it, based on the amount of resistance is here, it charges following an exponential, right? And it slowly reaches 100%. It's like a logarithmic increase. Every time you go out at RC time, you go up by a factor of 0.632, right? And then you go up by the same factor from before and before and before and before. So after 3 RC times, about 95%, et cetera, et cetera. And so you see the 1 minus E minus T over RC, the charging time, right? So this is a negative inverse exponent, right? E to the, right? So it's an exponential function, but it's a reaching the asymptote of 1, right? As E to the minus T over RC goes to 0. And then by the same thing, by discharging, it goes in the opposite direction. It drops by a factor of 0.632, or the inverse. 1 minus 0.632 is 0.368, right? So again, because the textbook kind of takes it easy on the mathematics, right? The decay time, the tau, right? The RC time, you have this decay over time, and the 1 minus E to the minus tau over RC, or in the other direction when you're charging. And this is how you like discharge stuff, going back and forth, right? So that's what I want you to remember. And then we have the RC circuit time in a heart defibrillator, blah, blah, blah. Remember all that stuff from the previous parts of the course, right? So we're going to go down back to the RL circuits. And it turns out that for an alternating current circuit, right, for an LR circuit, we know that the current through an inductor L cannot be turned off or on instantaneously, right? Because the change in current changes flux, and so you wind up getting an EMF, a voltage that keeps changing. So remember the EMF, right, that we often talk about in terms of basically equivalent to voltage, but you want to be careful and don't want to use all those words exactly the same all the time. But still, you have the circumstance where you have the same 1 over E time, right? The RL time, but instead of R times L, it's L over R. You see, L over R is the time that you're doing. So you have this kind of thing. The current, right? You want that it starts at, it gets up to this number, right? I0, I0, but it starts from 1 and minus E to the minus T over tau, where tau is L over R. You have the characteristic time constant. And so the current starts at 0 because at time 0, E to the minus 0 is 1. So 1 minus 1 is 0. And so what happens is you eventually have the current that goes all the way eventually up to 1, which means that you see R being the total resistance of the circuit. So the opposition of the inductor drops and drops and drops and drops until you wind up with the current at the highest level. So think of the L over R time as analogous to the RC time in a direct current circuit, right? And so the characteristic times depends on the inductance, the self-inductance, I guess, in this case, if you want to be really, really rigorous, as opposed to M, which is the mutual inductance, same difference, really, and the resistance, right? So your inductance, if it's big, then the amount of time it takes to change is greater, right? So you don't always want a big inductor, but you don't always want a small one either. It depends on where you get. You're cutting a battery out of the circuit. Right now you're talking about voltage again. So this is a voltage, and you can see that here, right? This is a series direct current circuit. But the inductor is a thing that shows up in alternating current circuits also, right? So you got to kind of be aware of how it's happening. So things are turning on and turning off. And so if you turn something off, you see how the energy dissipation as the current goes down by a factor of that 1 over E, right? 1 over E is about 0.368. So 1 minus 1 over E is 0.632. See? And so this is how you do that. You calculate the time and current in RL circuit. I suppose if we want, a more accurate way to say this would be an R over L circuit, but why add that extra time? Physicists and electrical people just naturally assume that you know, all right? So this is something that you might have to know conceptually, that RC circuit means you multiply RC to get RC time. But in an RL circuit, you have to divide R divided by L in order to get the RL time. Okay, it's an L over R. Weird, but true. L divided by R gives you that time, characteristic time constant. So the L over R time, as opposed to the R times C time, L over R. Now, if I said R over L, I'm wrong. That becomes 1 over tau, which is a different thing. Still useful, but L over R, L over R, tau equals L over R. Okay. Pay no attention to the person behind the curtain. Just pay attention to the fact that tau equals L over R, right? The characteristic time constant when you have an inductor and a resistor in a circuit is the inductance divided by the resistance. Okay. All right. So you can calculate the characteristic time and current in this kind of way. All right. Take a look at these. As you know, in the study guide, you are doing this kind of calculation quite often. All right. So you understand how this works. After 5 milliseconds has passed in this exercise, the current will be 0.183 angstrom. So, amperes, amps or coulombs per second. So it dies out, but it doesn't go to 0 right away. Is that good or bad? Okay, now let's go how if you, instead of doing an RL circuit in a direct current circumstance, which is described here, what happens in an alternating current? That's the thing that we plug our devices into the wall, right? So what happens? Remember what inductors do, right? Because it has this sort of inductive reactance, it kind of has this time lag thing. The graph of the current, right, which is in this green line, and the graph of the voltage, which is, graph of the voltage is the green line. The graph of the current is the red line. Notice how they're shifted. Right, they're shifted off in one direction. What's up with that? Why does that happen? Well, that's really interesting. What happens is that capacitors, inductors, they respond to DC voltage, but when they react to AC voltage, they do something slightly different. And in this chapter, it also talks about capacitors in AC circuits. So it's important. So here's that little symbol, right? Instead of a battery, like which is the long bar and the short bar, now we have this AC voltage source, like maybe your wall plug or something like that. And you have this little sinusoidal, like sine wave there, just to show people that, oh, that's actually an AC circuit. And it's the kind of thing that we have in our houses and the walls, right? Or in your doctor's office or in your dentist's office or wherever. And you have that kind of thing here. So if you have a voltage becomes negative, right? When it becomes negative, here, take a look at here, right? The current goes down. And then when at point B, the current gets to 0, the voltage is most negative, right? And it gets to 0 again, the current does, when the voltage is most positive. So this shift, you see it's off by a factor of pi over 2, if you want to talk about it mathematically, but it's a quarter of a shift a quarter of an entire wave off. It's just a little bit off all the time. 90-degree phase angles, what we talk about, pi over 2 being 90 degrees, right, in radians. So this is what happens here. The version of Ohm's law, right, the current through an inductor. Now, this RMS term, that's an interesting point. The RMS, the root mean square current. What does that mean? Let's pause for just a moment and have that conversation for a second, okay? Remember that your voltage or your current is passing through zero. It goes up to a certain amount, right, in AC circuit, and it goes to zero, and then goes down negative that amount, and it goes back to zero, and then up positive amount, and so on, and so on, and so on, right? So at any given moment, that voltage could be very low, or it could be at the maximum in one direction or the maximum in the other direction. But if it does it really fast up like that, and you count up how much voltage there is total, right? Not whether it's negative or positive, because a negative a certain amount plus a positive certain amount add up to zero. But all you care about is the magnitude and not the direction. Then over time, even though it does pass through zero, you still actually get voltage over time. So in any given cycle, if it's the AC, if let's say it's going at 60 hertz, 60 cycles per second, then every 15 milliseconds or 16 milliseconds or so, boom, you wind up with zero. But I don't live in a millisecond world usually, right? Usually I live in a world of seconds or minutes or hours and stuff like that. So in any given second, I'm looking at this thing, heck, even looking for a fraction of a second, my eyes cannot really distinguish between a steady light and a light that's blinking 60 times a second. Pretty cool, right? Now, our ears are pretty sensitive to that. We can actually, with our ears, we can hear like a tapping sound and stuff. But our eyes, we're looking at a computer screen. You've heard of the thing called refresh rate, right? How often does my motion here get reproduced? How often does it happen? If it happens at least 30 frames per second, right? If I go from here to here in 1 second, and the computer takes 30 different images, you can't really tell the difference between me moving smoothly and those individual things. Now, sometimes there's lag, right? In Zoom these days, we all understand that aspect. And so when the lag happens, then you can have the difference. Most movies these days, movie theaters, or if you're watching on some subscription service and so forth, those are filmed at many more than 30 frames per second, sometimes like 60 frames, sometimes even more, depending on if it's like high def IMAX or whatever. But then that requires your computer or your projector, whatever it is, to be able to refresh the screen that fast in order for you to see that smooth movement. And that's part of detector technology, or excuse me, display technology, which you can be involved in. But that's sort of the frame rate. So if you realize that in the way to calculate like how much voltage on average, or how much current on average gets to you, like over time, right? We don't use the term average in this kind of thing. We say root mean square. That means you take a square root and you have to do with the mean, and you do have with the square, that sort of thing. Okay, so if you haven't learned the term root mean square yet, take a look at it. Do some mathematical stuff and know what it is. So you'll see this RMS happening all the time, but it's a kind of steady state when you have things that are moving around. RMS, okay? Root mean square. All right, enough for an aside. I wanted to make sure that I got that out there in case you were curious as to what that meant. All right, going back to it. If you have the RMS current, I, through an inductor, L, right? Remember that there's that back EMF, right? And that's not something you normally want. It's almost like a resistance. In other words, when you send a back EMF, a resistance, right, minus L over the voltage back EMF is kind of like reducing the amount of voltage that's going forward, right? So it's kind of like a resistor. Same sort of thing, only it's not that the resistor or the inductor is absorbing it. It's just kind of creating this sort of backward flow, which you don't want necessarily. So you could want it depending on how you want to use your electric circuit. But the RMS current, I, right, through an inductor L is this version of Ohm's law. Now, X sub L, right, is this 2 pi F times L. So this is the 2 pi times the frequency. What is that all about, right? What that means is you're finding, do this circuit Kirchhoff loop rule and stuff, and you actually do this. If you were going to derive this, this is, calculus actually produces this expression. And you have this thing called the inductive reactance. So this is like the equivalent of resistance that a conductor produces, but it's called the inductive reactance. Does that make sense? So it's like ohms in the same way that like electromotive force is like volts, like voltage, right? It's the same kind of unit, but that's kind of the analog, right, between the alternate current and the direct current circuits. So it's kind of interesting. And alas, I would derive this for calculus, and you can kind of get this cool stuff, and you can see how they all fit together in a really beautiful conceptual way. But don't worry about it, because you don't need the calculus as long as you memorize this formula. Well, you can look up the formula, but you see, what I want you to know and understand is that when you have an RMS current, right, because you have this sinusoidal or alternating current thing coming through, and you have this current, right, and it's alternating, then the voltage, right, divided by the inductive reactance is kind of like the in a direct current circuit, I, current equals V over R, which is Ohm's law. Make sense? Okay, so here, calculate the inductive reactance, right, of a 3 millihenry inductor, and you have 60 volts and 60 hertz. So it's 60 hertz, right? And it's a 10,000 kilohertz AC voltage applied. So there's two different rates of AC voltage applied in this case, and you can see what the inductance is. When it's at 60 hertz, right, the inductance is 1.13 ohms. It doesn't seem like too much. But if it's at 10,000 hertz, 10 kilohertz, then it's at 188 ohms. That's a lot of lost current, shall we say. There's a lot of equivalent to have lost a bunch of current because you have a big resistor there, 188. So that's a large amount, right? And then how did the current go? Well, in the first section, you have this huge current because the resistance is very low. But in the second situation, you have a much lower current, right? Because you have this thing. So the inductor reacts very differently, but it's kind of useful that way. So how do you want to impede or reduce AC current flow, right? You can use this as a filter. Notice if you have like ever heard of high pass filters or low pass filters or something like that, you can reduce high frequency sound output, or you can reduce high frequency power spikes in your computer if you have an inductor in there that kind of solves or smooths out some of that that voltage spikes or the current spikes and things like that. Make sense? Okay, so remember here, this is really cool. In that circuit, there's no resistance, right? There is no resistor itself. Now, the AC current is not really big because you have inductive reactance. It acts like a resistor, and that's really interesting and useful. Now, what happens when you put a capacitor? Remember what we did when we had a capacitor before. And once again, you also have that phase shift again. But this time the phase shift is in the other direction, right? It's negative. I don't know if you want to call it negative 90 degrees, but it's a quarter. But instead of leading the current, right, the voltage follows the current. It's just a little bit on the opposite. I'm going to come back over here. Remember, in here, right, the voltage leads the current. As the voltage is going down, then the current starts to go down, right? Here, in this case, when the current starts to go down, that's when the voltage starts to go down. And when the current reaches zero, that's when the voltage is lowest, and so on and so on. So there's that lag. It's a different effect. And so you have another kind of thing going on here. The RMS current, again, the root mean square current in the circuit that contains only a capacitor, gives another kind of thing, right? It's capacitive reactance as opposed to inductive reactance, but you have the same basic effect. You have 2 pi f times the capacitance. But notice this is the reciprocal, right? Because there's that lagging, if the 90-degree phase is in the other direction as opposed to the one direction. And so you, again, do the derivation, right? And conceptually speaking, you have that beautiful connection, which is kind of exactly reversed. See here, right? The reactance of an inductor is 2 pi f times L, but the reactance of the capacitor is 1 over 2 pi f, the frequency, how many hertz, right, times the capacitance. And the capacitor reacts to impede the current also, but also just like the original resistance or the capacitor, the reactance of the inductor, you also have the units of ohms, right? So the more you have capacitor in there, the larger the capacitor exists in an AC circuit, the greater charge it can store, and therefore the greater the current that can flow as a result. See how that goes? Also, the greater the frequency, the less time there is to charge the capacitor. And so it impedes the current less. And so that's the exact reverse effect of the inductor. So here's an example of that. Right? Remember, we had the same thing about the 5. Instead of having a 5 millihenry inductor, you have a 5 microfarad, capacitor. And then you can go through the same stuff. I want you to take a look and enjoy going through that mathematics, right? And why does that matter? Take a look. A capacitor is different at the two different frequencies in the exact opposite way, right? So you can use capacitors to filter out low frequencies. So if you want, remember the inductor can use to filter out high frequencies. So you have like noise spikes or current spikes. You don't want them. You can cut them down. And if you want things are too low and they're kind of bouncing and they're and you don't want that, then you can use a capacitor and it'll cut out that low stuff. So you wind up with a nice mid-range. See? So it's really cool that you have both of these. And in a medical device, for example, sometimes you don't want those high, you don't want those lows, you want right in between. So you use both of those to regulate how smoothly it all works. And now finally, a resistor in an AC circuit. Now look at this, they are in phase, right? When the voltage goes down and reaches zero, the current also goes down and reaches zero, and then it come up and come down and come down. And this makes sense, right? Because the voltage doesn't store or doesn't like hang on to charge, right? It doesn't create a back electromotive force or anything like that. Instead, it just draws, right? Takes whatever voltage and then takes whatever current is flowing through and then makes your voltage happen and use it, right? So how does it work? They are phased exactly the same, so you don't have to make any extra this impedance thing, right? The reactance, inductive and capacitive, they're not relevant in this case because the resistor just produces resistance and it's in ohms, just like reactive and reactance, in inductors and capacitors. Pretty cool. All right, so we have now the ingredients we need, right? If you put an inductor in a DC circuit, we know what it does. If you put a resistor in a DC circuit, we already knew what it does from before, right? And if we put a capacitor in a DC circuit, we know what that does from before too. So now when we put them in an AC circuit, we also now know what they do. So now what happens if you put them all together into the same circuit? Let us find out, okay? This is sort of the last bit of circuit knowledge that I want you to know. Now, you're doing a lot, in all likelihood, of circuit stuff in labs, right? And when you have an AC circuit and you put them all together, a new thing shows up called impedance. Why do we have this extra word? Remember, you had all that ohm stuff, right? The inductor creates inductive reactance, and that's in units of ohms. A capacitor creates capacitive reactance, and that's in ohms. And then resistors are just in ohms, right? So they all kind of block or slow down the amount of current that comes through, right? Their individual resistances, though, don't just add. So there's actually kind of a complicated dependence on the frequency So you wind up with impedance as an overall thing. It's sort of like a summary of all the kinds of ways that current can be slowed down or otherwise reduced in a circuit. So you've got to know how it all works. Here's your V, right? This is the thing here again. Your complexity is somewhat mathematical, but I want you to know the concepts of happening. Imagine you've got this circumstance here, right? You have an AC source, like your wall plug or something like that. And then you have your maximum voltage is the V naught, right? And then you have sine 2 pi frequency times the time, right? So that's sine omega t basically, right? And so you take this and you put a resistor and you have an inductor and you have a capacitor. And each one of these in series, right, takes away, uses some voltage, and that affects the current. Remember that in the end, your current kind of all adds up to zero, right? You've used them all up. The current, use some current here, use some current here, some current here, or some voltage here, some co-voltage here, some voltage here, and your current stays the same, right? It doesn't go to zero, it stays the same. But if you add up all these things, then the voltages go to zero eventually, right? All of these together kind of going to junction should have the same amount of voltage eventually. So the combined effect of resistance and the reactances is called the impedance. So it's like resistance only if you just have a DC circuit. But impedance is what happens in an AC circuit. And so there's a kind of an Ohm's law to that, right? The IRMS, once again, there's that root mean square thing we were talking about earlier, equals the voltage RMS divided by Z. That's an Ohm's law, a kind of an Ohm's law. Same thing here. If you're talking just about the peak, right, the peak voltage, there's also the peak current, then that impedance does the same thing. You can use the same amount. It's kind of useful, right? The RMS is kind of what we normally talk about, but the peak, right, is a number that's easy to calculate sometimes, or easier to calculate than the RMS. So that's fine. So you have the different voltages across the different components. Oh, we've actually got some square root action going on here. Is that going to stress you out? No, it's not going to stress you out. Why? Because square roots are no big deal as far as mathematics are concerned, but you need to know why these things line up like this, okay? Notice that the voltage, right, is adding the square roots of V0R squared plus V0L minus V0C squared. So the voltages have this strange relationship. And most of that, okay, in the math you can figure out, most of that is because of the phase thing, right? Remember earlier we were talking, just a few minutes, the voltage leads, right, the current in the inductor, the voltage follows the current in the capacitor, and the voltage is exactly in phase in the resistor with the current, right? So as a result, you wind up with this unusual way of expressing stuff. That's okay. Not that huge a deal. You just have to remember this. And you know, I'm not going to make you memorize it. If you were going to become like an electrical engineer or something, you might use this a lot. But now you just want to know how this fits together. Okay. And this circuit stuff, like I said, it can be a little bit confusing if all you do is memorize equations, right? If all you're doing is memorizing equations, yeah, there's a lot to remember. But remember the concepts, right? The phase differences is what causes the math to be a little bit complicated. So as long as you're aware, oh, yes, you're in this circuit and this is a phase lag over this way and there's no phase lag that way and there's a phase leading that way, then you can just put it all together and you're good. Okay, so do not get confused. Do not be intimidated by the mathematics. Understand the concepts and the math will come. Okay, the math is not hard. It's just got little pieces that you got to keep in mind. Sound good? All right, that's my pep talk about math when it comes to circuits. Do not worry. Do not be afraid. It is all good. So the expression for the impedance can be expressed this way. All right, combining all those different variations, the impedance is the square root of the resistance squared of the resistor plus the quantity of the inductive reactance minus the capacitive reactance squared. Okay, and that becomes the impedance of an RLC series AC circuit. Okay, here's the relationships, the voltages to the current. Understand these things conceptually, please. All right, the calculations are fine. You'll do fine. But understanding this conceptually is what matters to you. And when you're doing medical devices, maybe someday that's what you're going to be doing, using a lot of medical devices. Maybe you'll be doing something like buying speakers for your stereo system. And you want to understand what all these terms are and why and which ones you want. This is all kind of cool. And all of your devices have this thing in the back. You'll see that there's a resistance of a certain number of ohms. Sometimes they'll just say impedance because they have AC involved in them. All right, so it's kind of fun. And you get to do this and get to know how it goes. Oh, resonance. Now here's something interesting. Look what happens, all right? If you have the voltage, right, is driving back and forth, as you can see. But if you find a specific frequency, there's a certain frequency of a series circuit that has an inductor and a capacitor in it. Okay, what does that mean? This 1 over 2 pi square root of LC is a resonance frequency, which means, right, there's a natural frequency that the circuit would oscillate if you don't have a voltage source. So let's say the voltage source is driving something, right? Fine. But if you don't have the voltage source, the circuit had something, it would oscillate at this frequency anyway. Isn't that funny? Yeah, it is funny. It's a kind of a strange thing. Now, you may remember from Physics 1 the concept of mechanical resonance, right? There's always fun to talk about. Now, there's not a lot of mathematical thing we can do about that, but later on, if you want to, go back to your Physics 116, right, and take a look at waves, like mechanical waves, and the idea of mechanical resonance, right? Just as a quick review, remember how when you were a kid, right, and someone was pushing you on a swing, or maybe you were pushing somebody on a swing, right? If you push someone on a swing and you push someone on that swing and you push them at exactly the same time they come back, then it gets bigger and bigger and bigger, right? Every time you push, you want it to get bigger and bigger. The way you make it bigger and bigger is to push it at the same rate that it's swinging back and forth. So every time it comes back once, you push it, or every time it comes back twice, you push it. But when you push it, driving, it's called, right, this oscillator or this thing at that frequency, then that oscillator frequency, what it does is it increases, it amplifies. It's at a natural frequency or resonant frequency. That's what resonance is. Now, the way to stop something from happening, right? Obviously, you catch it, but if you were actually just trying to do it, you just push it at a different rate. You have to push it at a rate that's not an integral multiple of the actual rate that it's driving the swing, and then you wind up eventually stopping it. It just goes down, down, down because all that it doesn't resonate. Does that make sense? So that's what you remember. Think about the swings, and you always push the swinging person when that person comes back to you. Not in the middle of the push, right? Not when it's over on the other side, because that's counterproductive. Not to mention you might whack your head. You don't want that, right? Okay, so that's that resonance frequency thing we're referring to in the mechanical world. Now we're talking about resonance frequency in the electrical world. And why is that cool? Because, take a look, right? When you have a radio receiver, it's an RLC circuit that oscillates at the resonance frequency. Okay, so let's say you've got, hello, there's I'm on my walkie-talkie thing here over, there's a frequency that you tune, right, to that point, and as a result, when you get that frequency, you tune it so you make it that it's a narrow band that allows you to just get the frequency in one wavelength, not too much lower, not too much higher, and then you get a stronger signal at that point. And getting the resonant frequency of that allows you to actually, like, for example, tune a radio or tune your walkie-talkies or basically communicate. It's really neat. having that, it's basically like a tuner. So what is a tuner? And then you have the impedance, you have all this stuff here, right? You have the power. Well, I kind of moved a little bit too fast here. Remember, there's a power factor, right? The cosine theta, which ranges from 0 to 1. The power in a circuit, remember, a power in a DC circuit, right? P equals I R, or V equals IP, excuse me, IV. P equals IV, or pi P equals IE, which is like how I like to remember it, or VIP, right? V times I equals P. The power, usually the current times the voltage. But if the current and the voltage are changing all the time, right, which they are, right, and they're out of phase, which they are also, right, that makes things so that the average power is affected. It depends on this cosine phi, okay? This phase angle, the resistance divided by the impedance, R over Z, right? Cosine theta is, cosine phi is 1 when you only have resistance, right? R over Z. But when you have both impedance and resistance, and they're different, which is the case in an RLC series AC circuit, then you wind up with this power factor, and it can affect the power in your system, right? Does this matter? Why is it important, right? Why do you care that power changes when you have the circumstance? Well, think about this example, right? The conductor and inductor and capacitor, right, basically transfer energy back and forth to one another. And so you wind up being able to filter and focus things, right? And so you get to get this radiation, right? The electromagnetic radiation, which we're talking about here, right, can happen and may even be desired. Like I said, radio transmitters and things like that, electromagnetic radiation, which is coming next. But if you want it not to be there, right, here's the physical example of what, when you have a wheel of a car that's going over a bumpy road, all right, what happens is that you have a bumpy road. Let's say the bumpy road, the bumps are exactly the right, same width apart all the time. You have a voltage sword. You drive the wheel up and down. So the shock absorber, you know, and I don't know if you've ever done this before. You just, you know, this happens in older cars more than younger cars, because in the more recent cars, what happens is you wind up dampening that out. So if you just have, see how there's this RLC AC circuit, you can wind up getting a big swinging back and forth thing with the resonance frequency, which most of the time you don't want, right, in this circumstance. But in the next part about electromagnetic radiation, you do want that. You want radiation to be discharged, which is kind of fun. And you want to get it right. Anyway, so in this circuit, right, you want a small resistance and a small amount of energy, and you want it to bounce back and forth, boingy, 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 right? You want it to have that oscillation. And when you have oscillation, then you can get waves. Then you can get things that you want to get changing back and forth, boingy, 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 and you want the boingy, boingy, boingy. Do you always want the boingy, boingy, boingy? No, you don't always want it to oscillate, but you want it sometimes to oscillate. So if you have an RLC circuit in an AC driven supply, you can create the same kind of resonance that in a physical circuit, like this car thing going bouncy, 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 you get bigger and bigger and bigger kind of waves, right? Remember that very often, you may have seen this in physics 116, very often resonance is shown to like show how you can really like damage something if it gets too big, right? But it can also see how like you can jump really high in a trampoline because you want to have that resonance. So those are the kinds of different things that you want to achieve depending on how you're doing things. And having the ability to do that in an electrical system is a very positive and desirable thing. Okay, but it won't be until the next lecture when we talk about electromagnetic waves that you can see why resonance is useful and meaningful. But we're not really going to go too deeply into that. Quite frankly, the key point is that you now know what happens in an alternating current circuit and what happens when you put a resistor in there and an inductor in there and a capacitor in there. You get a complicated system that is the kind of machines we use today, right? Whether it's like I said, a microphone amplifier speaker system that you might use to watch a movie or something like that, or whether it's a medical device where you have to get things just right, or whether you're trying to generate radio waves. Oh, this is great stuff. And I hope you've had fun, all right, learning about how these different circuits work. And I know individual devices and machines all have these different combinations of these different things. And I hope if you are curious enough that you go and take a look at a circuit diagram of something that you own. Could be a cell phone, could be a computer, could be an appliance, right? And look in the manual and see what the circuit diagram says. And you're like, oh, that's an inductor. Ah, that's a capacitor. That's a resistor. That's your AC power supply. Now I know what these things all are. Whether or not you use them on a daily basis, like knowing how they go, that's secondary of importance. The important thing is that you understand that these components do stuff and what they do and how they do them and how they impact your life and your use of these devices. Pretty cool, right? I think it's cool. Thank you so much for coming along in this cool discussion that we've had these past several lectures about magnetism, right? Followed by magnetism and electricity working together to create things like motors and generators. And then you have magnetic fields and then inductance, and then how that winds up going in circuits and winds up building all the cool things that we know today. Good stuff. Thank you so much for your time. Remember those transformers, more than meets the eye. Hope you've been filling out your study guides. If you haven't, go back to those, right? And we'll finish all that other stuff up. Remember, any questions, ask me, ask your recitation instructor, ask your lab instructor, write this all down. And there's a wealth of stuff all on the internet about all these things and how to do them. Okay, that textbook, as we've gone going through them pretty steadily, right? It's got some pretty good stuff in it. If you understand the things at the level of that textbook, you are all set. And remember, we're going to be doing some mathematics involved in here, but the math is just a piece of your learning. Know how to do it, all right? Know how to calculate it, but the concepts, understand them. Thank you so much. Have a wonderful day. We'll see you at the next lecture, okay? See ya.